In this class we will start with an optimization overview. Okay, so already you have an idea ki when we from the simplex or the LPP part of the syllabus ki whenever we talk about say any function or any objective function is given to us, we sometimes it is the problem ki we have to optimize it. Either we have to maximize it or we have to minimize it. Okay, with respect to certain constants, or it may be the case also ki there are no constraint. Okay, so here we are going to develop an overview of this whole optimization modeling. Okay, so this is a standard form of writing an optimization problem. Okay, so what is it written here? He optimize fj x for j in j subject to gi x, where it can be greater than, less than, or equal to b into bi for all I in I. Okay, so actually what they are trying to mean here, let us just see one by one. So here we are writing ki we are trying to say optimize f j then x. Okay, so what is our function here? Say in general we have the idea of a single objective function. Okay, but here they are talking about, whenever I am saying about the general procedure of writing the program, we are taking ki we can have more than one objective function where j belongs to say some capital set j, which is subset of some n natural number set. That means what it can, suppose I take if j equal to 2, then there are two functions f1x and another function f2x. Then we have to optimize both f1 and x and f2x. Okay, and if in case we have j equal to 1, then it is a single optimization problem. That means a single objective function needs to be optimized. Okay, and we are familiar with that one. In fact, we will be given only one objective function and we have to optimize it. Whenever this j is greater than equals to 2, then actually it is a multi-objective function or multi-objective program. Multi-objective, let me say program only here. So this is one thing. Another thing is that this x, if you just take care of that, they are saying x. What is x actually? This is actually, sometimes you can just consider ki suppose small n number of variables are there. Each of these variables are said to be the decision variables because they, depending on them only, the optimization is performed. Okay, so they are the decision variables. So actually we are considering a vector or an n tuple of decision variables. Okay, so this is written as a capital X here. That means in the sense whenever I take f j x, that means any function of all these decision variables. Okay, so any function of all these x1 x2 up to x and decision variables. Okay, and then along with this, what is said is subject to the constraints. Okay, and how are the constraints? Gi again x. Okay, either greater than or equal to, if let me just put a specific sign, or you may put like this also, no problem, some bi, let me write. Okay, so actually what they are trying to mean here, the RHS can be further modified. I am not going to there. What I want to mean here, here we are using another set of, say I running, or I belongs to capital I subset of n, where say suppose I has the cardinality, let me just say for suppose capital M. That means m constants are given to you. Okay, for each of I running from 1 to up to capital M, for each of them we will be getting at least one equation from here, and each of this equation depends on the function gi. Okay, that means say suppose I say ki m equals to 2, so that means there are two constants. One will be g1 x, say suppose I am taking greater than only, so b1, and another say g2 x, so suppose there I am taking less than equal to b2, like this. Okay, so here these are the constraints. So the constraints actually again are functions of the decision variables. As I already said, the decision variables will decide everything about optimization, and the constants which are to be imposed are given by these gi functions. Okay, so in totality we can write what they have written there. Okay, so let us go back to the tutorial here. So as I said ki you can write like this the whole optimization problem, and these are decision variables, these are objective function, these are the constraints. Okay. Now let me just have or give one simple example. Okay, so a carpenter makes tables and bookcases. He is trying to determine how many of each type of furniture he should make each week. Okay, so two things, he is making two objects, one tables and another bookcases, right? He is trying to do something, that means he is trying to do some sort of optimization. He try to determine how many of each type of furniture, that means either table or bookcase, he should make each week. He is trying to determine that. Subject to something, the carpenter wishes to determine a weekly production schedule or for tables and bookcases and maximizes his profit. So here lies the optimization motivation. Okay, that he want to maximize his profit. Okay. So the program or whatever problem is given to here now takes the shape of an optimization problem because of his motivation to maximize his profit. It costs $5 and $7 respectively to produce tables and bookcases respectively. Okay, the revenues are estimated by the expressions this one and this one, where XR1 is the number of tables produced per week and X2 is the number of bookcases produced per week. Okay, revenues are estimated by these expressions. Okay, now what he wants to do, he wants to maximize his profit. So how can we give a optimization problem structure to this one? Okay, so for that let us see what they are doing here. In this example, the problem is to decide how many tables and bookcases to make every week. Okay, so consequently the decision variables are the quantities of tables and bookcases. That means the decision variables are x1 and x2. That means x1 is the number of tables per week that he makes, and x2 denotes the number of bookcases per week that he makes. Okay, we assume this is a schedule, so non-integer values of tables and bookcases make sense. Okay, that means here x1 and x2 belongs to z plus non-integer, not only integer but also positive integer. Okay, we cannot take anything such as say 2.5 number of tables, like that we cannot take, obviously. So after that, the objective function is nonlinear expression representing the net weekly profit to be realized. Now what is the profit? Profit from the table and profit from the bookcases. Okay, so profit from the table is given by the revenue from the table, as they have already said here. What it is said, it is directly given ki the revenue estimated revenue obviously is given by this expression for the tables, and for the bookcases this. So his total profit is nothing but the addition of these two. Okay, so here you have this one, profit is revenue minus cost, obviously some cost is there. So this is for the revenue addition from the last part, and there is some costing obviously, so that has to be subtracted. So what is the costing? If you are taking $5 per table, so x1 number of tables, so 5x1 is your costing, and again similarly for that of the other furniture 7x2 is the costing, so you have to deduct this part. So this is your profit function. Okay, as they have written here, this is a profit function. Okay, so this he wants to maximize. Now you see, as they have given there are no constraint on this problem. Only constraint is that this x1 x2 should be integers, no further constraint. That means this gi thing less than, greater than, or equal to, none of this constraint is there up to what it has been said till now. So it is an unconstrained problem. Okay, now some variation is considered here. Let us consider the variation. The carpenter realizes a net unit profit of $25 per table and 30 per bookcase. Okay, he is trying to determine how many of each piece of furniture he should make each week. Okay, so here comes the first constraint, the total profit. Here what he is saying, the profit function is this, so the profit function can be infinite, nothing to put any barrier over his profit. Okay, but here he is a barrier key. Practically or originally what will happen, he cannot make any profit greater than $25 per table. Similar is the case for bookcase. Their profit cannot be or cannot exceed $30 per bookcase. Okay, so that means what? The first constant comes here, $25 plus 30. So actually he has to maximize this one now instead of this here. Okay, acha. Now he has up to 690 board feet of lumber to devote weekly to the project and up to 120 hours of labor. Okay, that means this is the material and this is the labor. Okay, he can use lumber and labor productively elsewhere if they are not used in the production of tables and bookcases. So 690 board of lumber he has. So these are his resources. Okay, the first part concerns about whatever his profit can be. So this needs to be maximized if x1 and x2 are considered to be the number of tables and bookcases per week. Okay, now are the resources which he have in hand, and this puts some restrictions over his production. Okay, so 690 is the material and 690 board feet, and 120 is the labor, 120 hour. Okay, he can use and lumber and labor productively as well. So that means these are the maximum limit. This is not the case कि he will use the whole resource here on making the tables or the cases and the bookcase. In case something remains, it can be used later. Okay, he estimates that it requires 20 board feet of lumber and 5 hours of labor to complete a table. Okay, and 30 board feet of lumber and 4 hours of labor for a bookcase. Okay, so as a whole he has 120 hours of labor. Out of it, again it gets divided between the two types of furnitures. So here comes a constant corresponding to this one. So 120 is the total amount of labor hour. It gets divided in between 5 hours of labor for table, total number of table x1, so 5 into x1. Similarly 4 into x2, 4 hours for labor for a bookcase, and total number of bookcases is x2, so 4 into x2. So total it will be less than equal to 20. Why this less than makes sense? Because they are saying that it is not the case that he has to use the whole resource here. In case the whole resource is not used, it can be used for future. Okay, so that's why this less than makes sense. If this line was omitted, he can use it anywhere else. Okay, if they are not used in production, if I omit this line, then obviously this less than equal to will be replaced by equal to only. Okay, and similarly for the lumber, whatever is given here, 690 is the total amount of lumber, out of which 30 board feet of lumber for each bookcase and 20 board feet of lumber for each table. So 20 into x1 plus 30 into x2, that should be also less than equal to 690. This less than is also for the same reason as I mentioned for the labor hour. Okay, and also here what is said, the x1 greater than equals to 4 and x2 greater than equal to 2. This is because of the contract which he is getting. What he has to do here, he has signed contract to deliver at least 4 tables. In the previous sum there was no limit how many tables or how many bookcases he is going to make, but here there is a limit. What is the limit? The limit is a lower limit. Lower limit means at least he has to produce 4 tables and at least 2 bookcases per week. So that means x1 cannot be less than 4. According to his contract, this cannot be. That means this gives this one. Similarly, x2 cannot be less than 2, which gives this one. Okay. So now you see, this is a constraint problem or constraint optimization problem, because you are getting a set of constraints. So now when he tries to maximize his profit, this cannot be just considered singly. It has to be considered or coupled with this system of constraints. Okay, so this is an example of constraint optimization problem. Now for classifying some optimization problems, let me just show it separately. So suppose, actually in any optimization problem, if I consider, it can be classified on basis of various parameters. Okay. So to begin with, say first of all what the example we just did, depending on whether constraints are present or not. If constraints are present, presence of constraints if is there, okay, then depending on this we get 2 types. One is unconstrained optimization, another is constraint optimization. The first example was unconstant optimization, so no constraint there, and the second one was a constant optimization, so constraints present. Okay, so this is on the basis of whether constraint present or not, we are getting these two types of these two categories of optimization problem. Next, depending on the integer the variables, the decision variables, if I consider, it may be integer type or mixed. Sometimes it is mixed, or sometimes it is also said to be mixed integer type. So the example which we just did, there was x1 x2 was the variables. So all these variables, if I take xn, they should all belongs to z if it is integer type. If not, then at least some does not belong to z, does not, or do not rather, do not belong to z. Okay. So this is the case for the decision variables. Then what else? Then depending on the number of objective functions, you can also classify it. Okay. Number of objective functions. As I already said at the very beginning, I am writing in short objective functions. If one, then single objective function or optimization problem, single optimization, single objective optimization problem. If not, actually better than one, then multi-objective problem, multi-objective optimization problem. Okay, sometimes it is also said as multi-goal optimization problem. That means more than one goals are set which are to be optimized simultaneously. Okay. What else? Now another important is on the basis of nature of the objective function and also the constant functions. The constants are also given as functions of the decision variables, so their nature of this, if all these functions and objective functions are linear in decision variables, then it is said to be linear optimization problem, or very well known is a linear programming. Okay, LPP as you say in short, linear in decision variables. Okay, and at least one of obj function or slash constraint function is nonlinear in at least one of the decision variables, in at least one of the decision variables, then obviously it is said to be non-linear type. Okay, in this case it is non-linear optimization problem, OPT problem I am writing in short. Okay, so till now we have given the whatever example we have done, we have dealt with the first one. If you just consider, let us go back to the material. This one is a linear problem, LPP, or linear optimization problem, so LOP also you can write, whatever. And the first one, this one, as you can see these are the non-linear terms which are present. This one, okay, this one, at least one also if it is present, then only it becomes non-linear. So the objective function is non-linear. Here there are no constant. Even if their constants are linear, this, because of the presence of at least one non-linear term, as I said, the whole problem becomes a non-linear optimization problem. And till now we have given or set only one goal. The carpenter was trying to maximize his profit only. No other goal was for his motive. Okay. So in this case, we were solving a single objective function or single objective optimization problem. Okay. So for the multiple one, we will give one example just now in a few minutes. Okay. So these are some of the classifications I think I have covered here. Whatever they are saying here, I have just already said. So I am not going to read it out again. So these are the things I already said. Okay. Another thing is the stochastic program and the dynamic program. Okay. Also, stochastic program, dynamic program, what they are saying is, suppose the constants which we are saying G(i)(x) so greater than equals to Bi or equal to Bi or less than equal to Bi, whatever, it doesn't matter. So if the constants here are such that they are depending on time, if this G(i)(x) are depending on time at least for one I, that is, at least say 3 constants are there, out of this only one constant is depending on at least for one I. Okay, depending on time, then the whole program, that means the whole optimization problem, becomes a dynamic optimization problem, OPT problem. Dynamic means depending on time, that means it's changing with time. Otherwise it is said to be in general a stochastic it's not stochastic, sorry, it's a static optimization problem. Okay, if not, then roughly it is said to be static OPT problem. That means static means it is not changing with time. Okay, so no need of taking care of the time. Okay, invariant of any time you set to solve the problem, static optimization problem. Another one type, as they said here, is the stochastic optimization problem. That means here the G(i)(x) is suppose equal to or greater than or less than whatever, if these constants for at least one I, G(i)(x), if for at least one I G(i)(x) is stochastic or probabilistic in nature, then the whole problem becomes a stochastic optimization problem, stochastic OPT problem. Okay, so the problem which we have dealt with is not at all a stochastic optimization problem, it is a deterministic optimization problem. If not, then deterministic optimization problem. Okay, so nothing uncertain about those constants. If there is nothing uncertain about the constants, then it is a deterministic optimization problem. If there at least one of the constants is such that uncertainty is there in the problem, then it is a stochastic optimization problem. Okay, now just go back here. And so these are the roughly all the classifications here. Unconstant optimization problem, just we started all just with an unconstant optimization problem. Here they are again giving an example. So suppose what we do in curve fitting, which you will encounter in the interpolation part of your numerical analysis syllabus. In curve fitting, what we do, a set of values or set of say coordinates are given, xi, yi, x1, y1, x2, y2. So suppose x and yn, these are all given to us. Okay, what we have to do, we have to roughly find out a curve somehow. I am not going to the procedure, such that says these are the points which are already provided to you in this box. You have to fit this as much closer, as much accurately as possible. Okay, so this is an curve fitting problem, it is also said on, and you are familiar with curve fitting because of your probability and statistics part of the syllabus in semester 5. So this is one such type of problem. So suppose a curve fitting problem. So here we know we have to fit a curve as much accurately as possible, depending on some numerical procedures, obviously, with the given data. So in that case, what is our objective? Our objective is to minimize the error. So how that we do it there? Say suppose I find out the curve as y equals to fx, and this is the data set given, it is given. So what we try to do, we try to minimize the error by calculating y minus yi, and then try to minimize this one, because this is the distance actually. If you just consider any point from here, so suppose this one and this one, this is say y1, and this is your y of x1. Okay, this is not clear, let me just show it separately. Okay, suppose this is the curve we have obtained, and suppose, let me just take only one point, so this one. So this is your y1, this much amount is your y1. Okay, and this one correspondingly is your x1, then so this point is x1 y1. Sorry, not this one actually, this is x1 0, just a pointer in this one. Achha. And now this one, so this point is x1 y1. Now I have obtained this curve. Okay, so if I now put x1 here, say I have obtained the curve y equal to fx, this one. Okay, by other numerical procedures. So this point is what? This is y equals to f of x1. Okay, so now if your curve is very accurate, so this gap should be very small. Suppose I have found out this one, and suppose anyone else has find out some other curve, say this one they have obtained. So suppose this curve one has obtained. So you can easily see that this gap is lesser than this gap. So this curve is better fitting. I have considered only one point, that is not the case. Obviously, you have to consider other data points also. All the data points have to be taken care of. Okay, so suppose it is the case for all data points, this curve is giving better result. Giving better result means what? This distance every time is becoming smaller. That means what? What is our objective? Every time our objective is to measure f of xi minus yi. F of xi is obtained from the curve you are just getting and putting the abscissa there, and yi is already supplied to you as a data set points. Okay, so I have to find out this absolute value every time for every I rather, and sometimes like this also we do, and sometimes we add up also. It depends on the procedure, as I already said, on the numerical procedure which we are following. Okay, so whatever, if you take singly or if you just add them up, okay, so as to take the average, we want to minimize this absolute value. So this is, you see, is itself an optimization problem. Now you see there are no other constraint, nothing other constraint is there to fit a curve. This is an optimization problem without any constraint. So this is an example of unconstrained optimization problem. So this is what they are saying here. Now integer optimization problem, I have already said an example of it. So there are various items to be taken on the space shuttle. Unfortunately, there are restrictions on the allowable weight and volume capacities, obviously. So suppose there are m different items, each given some numerical value cj and having some weight wj and volume vj. So what we are actually trying to do, we are actually trying to load different types of materials. Okay, so there are m different types of materials we have to load. For each of this, there are two things we have to take care of. One is some cj attached with it, say one particle, any particle, ith particle if I consider, particle or ith material, let me say, not particle but ith material if I say. So with it, there are two things which has to be taken care of. One is the ci, some weight or some value attached with it, another is weight wi, another is weight a volume vi. Okay. ci is any type of numerical value can be attached. Suppose you can just say about it's what anything, any specific gravity or something like that. Okay, or you may say number it depending on its priority, how it to be used, how essential it is. Okay, there are many ways you can attach a numerical number with it. So this ci accounts for that. This is wi, weight, and this is vi, volume, for ith particle or ith material. Okay, and this is true for any of this m materials. So I runs from 1 to up to m. Okay, so as soon as I mention this weight and vj, so here comes some optimization, some constraints. Okay, now what we will try to do, suppose the goal is to maximize the value of the items that are to be taken without exceeding the limitations of weight or the volume. Okay, so whatever numerical value I am attaching, I have to maximize that. Okay, under the constraints or subject to the constraints of the provided by the weight limitation, the total weight that can be carried by the space shuttle is capital W, and total volume that can be fit inside the space shuttle is capital V. Okay, so here where they are formulating the model like this, let yj equals to 1 or 0. So yj is taking two values, either 1 or 0, so it is a binary variable. So first and foremost of all, it is taking only integer values, 1 or 0 are integers. Yj equal to 1 when if item j is taken in the space shuttle, and it is 0 if it is not taken. Quite obviously, if it is present in the space shuttle, then 1, not present, 0. Now what is our problem maximization goal? Maximize CJYJ. So m number of materials are there, so here the summation is from 1 to m. For each material, what I will see ki whether it is carried or left aside, that means whether it is in the space shuttle or not. If it is in the space shuttle, then yj will be 1, otherwise 0. And then some numerical value is attached to it. Okay, so now you see, I will try to maximize those numerical values, that means numerical values corresponding to those materials which are carried. Suppose I say ki suppose y5 is 0, that means the fifth material is not carried, then definitely I will not consider c5 because it is not at all carried. Why should I consider the numerical value attached to it? Because they are trying to do what? They are trying to maximize the value of the items that are to be taken, not the items that are not to be taken. Okay, that's why I am considering this Cj into Yj. If say suppose C5, as I said, a Y5 is 0, then C5 will not be there. So suppose that there are 6 items total, so C1 plus C2 plus C3 plus C4 plus C6 will be there. C5 is not there, like that. Okay, as a subject to the total volume, that means for each of this, again the same thing. If the fifth material is not carried, so excepting V5, everything will be there, and total weight will be say V1 plus V2 plus V3 plus V4 plus V6, that should be less than equal to capital V. Similarly for the weight. Okay, so this is the thing. See how simply by just taking this one tactfully, I can consider whether the material is taken or not taken. So these are your decision variables now. Okay, so now this is the decision variables. So here they are actually discussing the utility of using these types of binary variables. They provide some flexibility in modeling. They can be used to represent yes no decisions quite obviously, as we are using here itself. Yes, if it is a material is carried, yes. If the answer is yes, then yj 1. Then only you count all its volume, its weight, its numerical value attached. If no, then no need of taking its weight, no need of taking its volume, no need of taking its numerical value attached. Okay, so that helps us to decide one. Also in some cases it will be used as the on or off state of any matter. Okay, another thing where it is used, these binary variables are used, is that the variable x can be restricted to the value 0 and a. That means any interval you are choosing, you can restrict your decision variable to lie within this range only by using suitable combination of binary variables. Okay, so how it is done? By using the binary variable as a multiplier. Here they are giving an example, say x equals to ay if you take, where y is 0 or 1. So if it is 0, x is equals to 0. If it is 1, then x equals to a. So you see, one thing I just said a bit wrong here, not within the range, but only this specific values. So let me just correct it here. So that what they are saying is this only, say suppose you are taking one value 0 and another value a, I am taking this variable, binary variable, in such a way so that the original variable x, which needs to be considered in any problem, should be attaining only the value 0 and a. Say suppose I am not using the binary variable, then what I have to say? I have to break it. So suppose x equals to 0 I have to take, again I have to take x equals to a, but I cannot write them both together, right? So if I want to write them both together, I have to multiply it, or I am not saying it is the only procedure, I am saying it is only one of the procedures to multiply it with the binary variable. If it is 0, then you get 0. If it is 1, you get a. So these two possibilities are covered in a single possibility by using a binary variable. That is what they are trying to say here. Okay. Similarly, as I said here, another illustration restricts x to be either in the interval ab or to be 0 by using the binary variable. So now instead of taking single values, you can restrict or you can choose your variable to lie within a range. As I said in the first earlier case, is within the range or outside the range. That means not within the range. Okay, that means that will be assigned with a 0. Okay, so suppose I want this one. If y equal to 0, then it is 0, as you can see, because this and this becomes 0, so ultimately this x is going to be 0. But if it is y equal to 1, then definitely your x variable is lying within a to b. That means your x variable is lying within any interval you are taking a to b. So here also you are just converging or just you are just writing two possibilities together. Either your variable is 0 or your variable is lying within a specific range. That means either x 0 or x belonging to say ab. So simply you can, if I want to take this closed interval, you have to put less than equal to, done. Otherwise, if you put this small open interval, then no need of taking this less than equal to sign. Only strictly inequality sign you have to take. So this is it as a now. Let me just so this is further discussed about the different other utilities of the using the binary variables can be more fully appreciated when the object is to approximate a non-linear function by a piecewise linear one. Okay, specifically they are considering this figure. So this structure, this figure is this curve. Okay, this cost function curve, suppose. So as you can see here, or they have shown here rather, from within this structure the curve is decreasing in nature. Okay, starting from 0 up to a1. Again, from starting from a1 up to a2, the curve is again increasing in nature. Okay, again starting from a2 to a3, the curve is again decreasing in nature. So the curve is not at all monotonic, but it is piecewise monotonic. Okay, so within 0 to a1 it is increasing, within a1 to a2 it is decreasing, within 0 to a1 it is decreasing, within a1 to a2 it is increasing, and from a2 to a3 again decreasing. So it is changing its nature rapidly. So this rapid change of nature, if I want to consider, obviously you can see from here, definitely is a non-linear function. This y equal to fx curve, whatever it might be, it's a non-linear one, because if it is linear then you should got a straight line. You are not getting it, so it is a non-linear curve. Okay, so whenever any problem is such that it is incorporating this type of function which is changing its nature every now and then, okay, then what it will be better to approximate it by piecewise continuous functions. So what I am doing, it is a non-linear curve. So in most of the cases for solving non-linear optimization, what we do, we approximate it by an accurate linear function. I am not going to discuss about the methods now, but the thing is that we want to approximate it by something which is linear. So this non-linear function y equal to fx is approximated by a linear function. Now as soon as I want to approximate, the problem is that due to the sudden change, or rather the rapid change in the nature, because of the rapid change in the nature, what will be the nature of the linear curve? It will be piecewise continuous. So this one for tackling the first part, again this one for tackling the second part, and again the last one for tackling this one. Okay, so as a whole, what you are getting, from 0 to a1 with a slope k1 you are drawing a straight line. Again from a1 to a2 I am drawing with the slope k2, and again from a2 to a3 I am drawing with the slope k3. Now let us see this pictorial. This is the pictorial version I discussed, but now we will see this what we are doing. We are trying to linearize, but as soon as we are trying to linearize, we are facing a new problem. That means we have to now consider or rather tackle with a piecewise continuous function. So as soon as I am getting piecewise continuous functions, Let us see how these binary variables will help us to write them out. Okay, piecewise means in each and every part of the range from 0 to a1, I have to get a line of the slope k1. Okay, again from a1 to a2, again another line of slope k2, so another functional expression. Again from a2 to a3, again another functional expression to write a line with slope k3. So here lies the way out. So for this approximation, one problem is to find the minimum of the function. Suppose this is the function which is to be minimized. Okay, so this one is given. So b1 plus k1 into x minus 0, this thing, b2 plus k2 into x minus a1, this thing. So as you go on reading out, you see each and every part you are dealing with a branch of the function. 0 to a1, this is the expression. a1 to a2, this is the expression. Again a2 to a3, another expression. Okay, so now what they are doing, they are taking help of some binary variables. They are taking, or rather considering new variables, x1 as x minus 0, x2 as x minus a1, x3 as x minus a2. So x is a running variable, right? X running. Okay, Achha, this running variable, with the help of this running variable here, I am just dividing this whole thing into 3 new variables, x1, x2 and x3. Okay, for each of the 3 intervals we have to consider, and then use the binary variables y1, y2 and y3 for each of the 3 intervals. How I am writing? x1 line between 0 to y1 a1, because if y1 is 0, then x1 is 0. If y1 is 1, then x1 is running between 0 to a1. But what is x1? x1 is x minus 0. So here if I decode it, either it is this one or x1 is 0. But x1 is 0 means x is 0, because as we have written, x1 is nothing but x minus 0. So everything ultimately comes in terms of x. Similarly for x2 lies within 0 to y2 into a2 minus a1, and similarly x3 lying between 0 to y3 into a3 minus a2. You just break, so suppose x2 is what? X minus a1. So if I break it here, if y2 is 0, then x2 is 0, no other possibility. But otherwise what it will be? Otherwise it will be x minus a1 sandwiched in between y2. y2 is, I am taking to u1, that's why I am getting it. So a2 minus a1. So this cancels. So you get x less than equals to a2, and on the left hand side what I am getting? 0. So for that one, if I consider, so it will be a1. So your x is ultimately lying within a1 up to a2, in case y2 is non-zero, and if 0, then x2 0. x2 0 means only you are getting your x equals to a2. That means this, only this equality keeps then. Okay, so once I write like this, similarly the last one, so once I write like this, what I am getting? Achha, because we want exactly one xi to be acting at any one time. Obviously, whenever we are saying, so suppose my point is somewhere here, that means what? My correspondingly in the original curve somewhere here. That means at a time it is on this increasing part. That means at a time it is between a1 and a2 abscissa. Similarly here. So at a time means what? Obviously, if I say my point is here, definitely you know that then the point is not here in anywhere or not here anywhere. Okay, so definitely if in that case y2 is active, so I have to consider which interval? This interval. So as soon as I am sure that I have to consider this interval, because my points, the capital P is lying within that interval only here. Let me just use something else. So this is the point which is lying here. Okay, so this one. So I become sure that this is no longer required. Again, this is no longer required. So as soon as I am sure that this part and this part is no longer required, that means what? I have to take what? y1 0 and also y3 0, and quite obviously y2 equal to 1. y2 equals to 1. So any one at most one of them, not at most, exactly, neither at least not at most, exactly one of them should be considered at a time, either this interval or this interval or this interval. Not the case कि two of them will be active, not the case कि none of them will be active, not the case कि all three will be active. Only one at a time will be active because of this very obvious fact ki the point whichever you are considering at a time can lie at a single point or at a single position, and the position lies in any of these three parts at a time. Okay, so this y1 plus y2 plus y3 equals to 1 very easily fits here, because what you are telling ki your yi is a binary variable. So what are the values possible? 0 and 1. So if 1 is 1, then definitely other two should be 0. Also, if I take all three 0, then definitely this will not be satisfied. That means what? You have to take at least 1 to be 1. So at least 1 is required because this is 1 on the right hand side, and at most 1 again because all these are binary variables. Okay, so as a whole you are getting exactly 1 of y1, y2, y3 should be active. So as to get the practical idea ki of this point existence in any one of this part. Okay. Now the only one of the xy is active at any one time, our objective function becomes again cx. So what was the function which was to be maximized or which was to be minimized, whatever they are said to be minimum, so minimized. So this was their objective function. See, before we have to write the objective function as a piecewise function because this was the thing. Actually this was the main problem given, but as I said, for the non-linear we approximate by a linear problem. So this one we use for our purpose for linearization, and corresponding to this one we are getting this cx function, this for the first part, this for the second part, this for the third part. So I have to deal with the cx as a whole. So using this binary variables, you can see that this objective function now can be easily written as this one. I just rub this all out. This cx is taking this simple part or this simple expression rather. You see everything is coming inside. The first part, okay, y1 into this b1 plus k x1 k1 x1, because x minus 0 I have taken to be x1. Then this part y2 into b2 plus k2 into x2, so this one. And then last one y3 into b3 plus k3 into x minus a2 is taken to be x2 x3, so this 3. Okay, and as I said ki exactly 1 will be active, so either this part is active or this part is active or this part is active, depending on whether on which part your point is lying. So quite easily you can write it. See, these three branches just combine to form a single branch, a single thing. Exactly the same thing remains. Okay, it is the utility of using the binary variables here. Okay. So now the model in example 3 is classified as a mixed integer programming problem because only some decision variables are restricted to integer values, obviously. And then they are saying something which are related to the solution of it, which we are not in this introduction part, we are not going into the details of it. Okay, as we proceed we will be learning whatever procedures are there up to our syllabus. Okay, so I'm just skipping this part for time being. Okay, so the only thing is that, as I already said, keep some of the variables are integer and some are non-integer, obviously, then your problem becomes a mixed integer programming problem. Okay, in the next class I will start with the multiple objective programming problem example. Okay, I will just give this example, I will discuss this example in detail in the next class. Okay, so let me stop.